Maybe. All right, so today I want to talk more about this optimization with one choice variable. It comes from chapter 8 of the Sid Sater textbook. All of chapter 8 is just about this practically. And we're going to do it today. We'll be done with it by today, I expect. If not, a little bit next week. But so what does it mean? It means I have an objective function. Remember, the thing that you're trying to maximize is called the objective function. The thing that you're allowed to choose in order to maximize it is called your choice variable. And the set from which you must choose your choice variable is often called the choice set. So really, those three things define the problem. The problem is maximize or minimize, but in this case, maximize the objective function subject to the constraint that your choice variable has to be taken from the choice set. Okay. How do you solve a problem like this? Well, use the first order condition, which is that f prime of c is equal to 0. You're searching for something c where f prime of c is equal to 0. That was called the first order condition. And then the second order condition, well, that depends on if you're maximizing or minimizing, but if you're maximizing, it's f double prime of c should be less than 0, and flipped if you're minimizing. So let's get some examples of that. A lot of you already know this. You would already be able to maximize or minimize a function. I still want to talk about it, even if it's a review, because when we go on to multiple choice variables, it's good to have a good foundation, because some things will change when we go to one choice variable to two choice variables. Some things won't change. And I can at least kind of hammer into you how to do the things that don't change. And that's your foundation. Okay, let's talk about this graph. I don't think I've showed you this. This is just some generic function f that I'm thinking about maximizing. Can you guys look at this and just tell the answer? What would it be? Here's the problem. Maximize the function f of x such that x is taken from the interval a to b. Can you just sort of look at this and maybe even you would be able to point at what the answer is, right? I've given you no way to describe it, but hopefully it's just visually obvious that it's this point. You can see my cursor. There's this kind of one point here at the top. The answer in some sense is both whatever value of x would be right here that corresponds to this maximum, and also the maximum value itself, which would be the corresponding point on the y-axis, right? This value of x and this value of y, they sort of both together define the solution. I will say usually when I'm talking about solve the problem, I mean solve for the x rather than solve for the f. You know what I'm saying? If you give me f of x, that's good also. But giving me x, I think is the most sure way to solve a problem like this. I'm really asking, what value is this x? Okay, so how do you do it? You use the first order condition. What does it mean? It means the derivative at that point, whatever this special point right here is, the derivative that should be 0. That's the first order condition. It looks like this. So I'm showing you now an interior solution, first order condition, f prime of c, where c is this point, evaluated at f prime evaluated at this point, c should be flat. That's kind of what it means to be a maximum, right? We still don't, if all I told you was that f prime equals 0, that wouldn't tell you if it was a maximum or a minimum. And that is why this is just a first order condition. To think about whether it is truly a maximum, you have to use a second order condition. And remember what that is? It's that f double prime is negative. F double prime is negative is the same thing as being concave down or a concave function. So here's this little description of that. Now I'm showing you the second order condition for a local maximum. Okay, now we'll get technical in the terms of what does it mean to be sufficient versus what does it mean to be necessary for a second order condition. What I've drawn, what I have here in blue, is not the necessary, it is the sufficient second order condition for local maximization. That means if I have some point C, which has already satisfied the first order condition, you can't even talk about the second order conditions unless the first order ones are satisfied. Okay. So let's say C is a point where the first order is satisfied. And the question is, can we be sure it is a local maximum? That's what sufficient means. You should think of sufficient as like a proof. It's like a way to prove that it is a max. And I'm arguing here that f double prime being less than 0 is a way to prove that. The only way that could happen is if the slope was increasing before this point and now is decreasing afterwards. That's what concavity essentially means at that point, and that means it has to be a maximum. It can't be any other thing. By the way, I'm assuming that it's differentiable. I assumed that way back here. F is differentiable, okay? Obviously, if F is not differentiable, let's say it started to go down and then it jumped up here for some reason, that would be weird, but it's certainly not differentiable. Okay, do you guys understand what that means? Sufficient second order condition. It's like a way to prove that it's a maximum. Also, why do you think I say local max instead of global? This point C is not the global maximum of this function, is it? Local just means in some neighborhood. Well, sure, in some neighborhood, C is a maximum. F of C is a maximum. But if you just go a little bit further this way and then up here this way, now it starts to be getting higher than this point. Therefore, C is not a global maximum of this function F, but it is a local maximum. So because it's a local maximum, that means it might be an interior solution of this problem. But we're still not done. In general, you still just can't say, well, the answer is C because it's a local maximum. Why not? Well, there could be more than one local maximum of a function. A function could have several local maxima, in which case you still have to check which one it is. Also, there might be a corner solution. If you have a corner solution, it won't necessarily be a local max, but it could still be a solution. I'll give you an example that's like that later. Okay. You guys have any questions about what it means to have satisfied the sufficient SOC, in this case stands for second order conditions? Okay. Here's the necessary ones. It doesn't look any different, really. The necessary is, the only difference here is that it's less than or equal to 0. And what does that mean? You should think of a necessary second order condition as, well, if I have a point that doesn't meet that, then it's definitely not a maximum. Okay? It's not saying that I'm proving it's a maximum. It's saying you should think of the necessary condition as something which, if it isn't met, then it tells you something, right? The necessary condition, if it's not met, then it tells you it's not a maximum. And that's true here. If the second derivative, if this were not met, that means the second derivative would be positive. And that actually means it would look something like a bowl, which means it's definitely not a maximum. It would look kind of like here. See this region I'm highlighting with my cursor? That sort of looks like a bowl. Like if you poured water in it, it would stay there in the bowl. That's what would be happening if F double prime were positive. So of course we can see that that's not the case. And in general, these necessary conditions aren't as important. I don't think they're going to matter as much, but I just want you to know what they are. Later on, it'll be more significant, sort of the difference between the two. Right now, the only difference is you look here. Here is just less than. Here is less than or equal to. That's the only difference between necessary and sufficient second order conditions. You might ask, well, what really can happen if f double prime is equal to 0? Is there anything interesting that happens to some function at f double prime equal to 0? I think the answer is yes. Think of the function negative x to the fourth, right? Where x could be anything. What is the maximum of the function negative x to the fourth? I'm asking you right now, actually. Give me an answer if you can. Here, I'm asking in the chat. What value of x maximizes f of x equal to negative x to the fourth? This is a question you guys can answer. Just by thinking about it, you can answer it. I'm sorry I'm eating. I don't know why I'm eating. I would not normally eat in class. Apologize. Nobody has an answer to this?
Would it just be 0?
Yes, thank you. The answer is x equals 0. Okay, let's think about the second order conditions. Are these, what is f prime of x is the derivative of that? That's actually negative 4x cubed, isn't it? Let's think about f double prime of x. That's equal to negative 12x squared. So what is f double prime, the second derivative evaluated at 0? It's actually 0. This is one of those cases where it matters. The difference between the necessary and the sufficient conditions matter. Because the necessary condition is satisfied, f double prime is less than or equal to 0, because 0 is less than or equal to 0. But the sufficient conditions are not. The sufficient second order condition is that f double prime is less than 0. 0 is not less than 0. So you have this case where you really wouldn't be able to prove that f is maximized at x equals 0 using the sufficient second order conditions. But what could you do? You could say, well, x equals 0 is the only point that satisfies the necessary second order conditions. I should say first and second order, right? X equals 0 is the only point that satisfies the first order condition. And it does satisfy the necessary second order condition for local max. So if we think there's a maximum out there somewhere, the only potential answer for it is 0. That's another way, it's a kind of another route of thinking about this kind of a problem. Okay, I just demonstrated that. I used that example to demonstrate there can be a maximum that doesn't meet the sufficient, but it has to meet the necessary. If it doesn't meet the necessary, it's not a maximum. Okay, I think I've spent enough time on that. But actually, if I haven't, ask me questions about it now, so I can try to make more sense for everybody. Okay, next slide. Just to summarize this little graph that I've drawn, x equals c was satisfied the first order condition. It satisfied the necessary second order condition. And we know that the corners, FA and F of B, are smaller than F of C. This is going to matter. If you're doing an optimization problem, so like what if instead of if the region wasn't between A and B, but it was between, let's say, like A and 2B, so that right endpoint of this interval doubled from B to 2B. I don't know exactly what that would be. We go up somewhere over here. Your answer would no longer be x equals c, would it? It would be whatever the rightmost endpoint is. That would be your answer to this problem, this maximization problem. So actually, the argument I'm making now is that C is truly the solution to your problem only when the function is greater than the function evaluated at either of the two corners. That's when you know it is indeed the unique solution to the problem. So I guess I want you to have some practice going through the motions of this with some real numbers. And I'm sorry, I haven't actually given you a real function yet. We're going to do that, I think, just now. All right, here's a method. Sorry, before I give you an example, I want to describe the method. Then we'll get to the example. Okay. If this function is twice differentiable on the domain defined by the choice set, we're going to say the choice set is some interval here between A and B. Here is a method for maximization. I'm not saying it's the only one. I would just tell you this one. First thing you can do, like step one, find all critical points of F using the first order condition, F prime equals 0. You're searching for some C that satisfies F prime of C equals 0. That's step one. Step two, test to see if any of these points that you found satisfy the necessary second order condition, F double prime of C less than or equal to 0. That means they might be maximum. What you say, why not use the sufficient? Well, the sufficient would be a nice way to prove that it is a local max. But right now I'm just giving you a method for maximization. And in this particular method, you don't have to prove that something is a local max. Rather, you're just trying to see what could be a max. And the thing that could be a max are things that satisfy the necessary second order condition. So that's step two. Step three, this is kind of crude. You just calculate the value of the objective function at all critical points that satisfy the second order condition. You know what I mean by calculate the value of the objective function? I mean, you just plug it in for F. Whatever F is, you plug in the values and see what the objective function is. Do that for all the critical points that satisfy and the two corner solutions, A and B. And then once again, this is crude. You just look and see whatever gives you the highest objective function, that's the maximum. If there's more than one, let's say there's a tie. What should you do if there's a tie? Like in terms of economics, what are we thinking about in those cases? Generally, we would say they're both maxima, plural. You can have a multiplicity of maximum in a problem. That's okay. Okay, I think we're ready. Oh, by the way, for minimization, the only real difference is that this sign here is flipped. And and in step 4, you're looking for things that are the smallest. The 2 and 4 change for minimization, but that's it. Okay, now are we ready? Now are we ready to do a first very simple example? I even put the word simple here just to ease your mind. Here it is. You guys think you could do this? And then have me help you if you need it. Keep getting texts. Anyone can talk, can say the answer out loud or put in the chat. I'd rather you say it out loud, but. First thing you should do is take the derivative of the objective function, okay? Take the derivative of the objective function, set it equal to 0, and solve. Solve for x. That'll give you the critical points, which I often call C, but you don't have to call them C. The book called them C. And then it's just a matter of, if it's the only critical point, you might think, okay, maybe that's the answer. Convince yourself it's the answer by evaluating it and comparing it to the two endpoints, the two corners. X equals 0 and x equals 10 are the two corners. Anybody have an answer?
10/4.
10/4. That's 2.5, right? Yes,
Yeah.
that is correct. Good answer. Who said that? Jonathan? I can't tell who said that.
Yes, it was.
All right. Yeah. So you did what I said, right? You took the derivative, set it equal to 0, and then you do this. The derivative of this function is 10 minus 4x. Set that equal to 0. That's satisfied with 2.5. Okay, let's check the second order conditions. Right now, let's just check the necessary ones. And that is that the second derivative is negative or 0. It is negative. In fact, it's always negative. So clearly it's negative for x equals 2.5 because it's always negative. That means what you found in step 1 could be a maximum. Think about what's happening at the corners. Well, at x equals 0, f of 0, if I plug x equals 0 in here, I get 10 times 0 minus 2 times 0 squared. That's 0. You guys get what I'm saying here? F of 0 equals 0. Then plug x equals 10 into f. If I plug x equals 10 into f, I get 10 times 10, which is 100, minus 2 times 10 squared. That's minus 200. 100 minus 200 is negative 100. So I can conclude in step 4 that the solution is 2.5 because the objective function, if I compare 20.5, 0, and negative 100, oh, I'm sorry, I don't think I talked about this, but you can plug x equals 2.5 into here and get, this becomes 25 minus 2 times 2.5 squared, 20.5. If I did the math right. But that's the answer. The answer is x star equals 2.5. I put a little star here to indicate it is indeed the solution. Not just a candidate solution, but the actual solution to this maximization problem. Guys have any questions about that? How we got to 2.5?
I have a question.
Sure.
So when you're looking at the corners, like f of 0 and f of 10, what exactly are you checking for? Like, I'm trying to figure out how to ask this. So, because the solution is x equals 2.5, right?
Yeah. I think I can answer. You said, what are you checking for? The answer is, I'm looking at this number right here. Is there a way for me to just highlight this? No, there isn't. I wish it, is there annotate? Does that do it? What does this do? This number right here, you can't annotate.
Yeah.
And this number right here. I'm looking at those two numbers and I'm comparing them to, I'll do in red, this number right here.
Yeah.
And the fact that this number in red is bigger than these two numbers in blue, that's all I need. That's all I need to convince myself of.
Okay, that makes sense.
That's how I know the answer is 2.5.
Okay.
So this was kind of an easy problem where you could maybe imagine this, you could visualize this function or graph it or something and really easily tell. I would like for you to be able to do this for any function, at least any function that you know how to take the derivative of, which is a lot. I mean, exponents, logs, powers, quotients, products, all that stuff. You can use this method just to solve a maximization problem, because what you really need to do is create these first order conditions and solve for them, then check the second order conditions, evaluate the objective function, compare it to the corners if there are corners, which generally there will be. By the way, if there's no corners, if like, let's say x could be any real number, some of what I say here doesn't quite work because you can imagine a function that just grows indefinitely in one direction. Or yeah, also if it's not differentiable, if it has an asymptote at a point, right? Where it just goes off to infinity and then it jumps to negative infinity and starts coming from the other direction. That's a point of being non-differentiable, which means this method won't work. This method is for differentiable functions and what you might call a compact choice set, where we have edges that you can check. Okay. Should I go on? Make sense, Amina?
Yeah, it does. Thank you.
Oh, those things are still there. Interesting. I think I can unannotate them, right? Clear. Clear all drawings. Yep. Cool. Yeah, Zoom usually works pretty well. How about this one? Sorry for all the messages. How would I solve this example? Maximize over the interval 0 to 10 the function x squared minus 5x. I'll even get you started here. The objective function is x squared minus 5x. We find the critical points here. It's the same critical point as last problem. X equals 2.5. Remember, critical point just means f prime is 0. The book might also refer to them as stationary points. But I like critical point. What do you guys think? Next step is to think about the second order conditions. I don't know how to turn that off. That was muted. Now it should be muted. What do you guys get? What are the second order conditions here? The second derivative is
2.
2. And that should be negative. But wait a second, 2 is never negative. So that tells us that the thing that we found in step 1 is not a maximum, right? If the necessary SOC are not met, then you know it's not a maximum. What does this mean? There can't be an interior solution. If there were an interior solution, interior just means not at the corners, then it would have satisfied both the first and second order conditions, and there's nothing that does. My internet connection is unstable, warning me. So the only thing left are to think about the two corners. The objective function at the left corner is 0. The objective function at the right corner is 50. 50 is larger than 0, so that's the solution. The solution is x star equals 10. Did you guys get that? This was a case where you had to use the corners. And of course, it kind of makes sense. Here's a quadratic function that opens up, parabola that opens up and close to 0. It actually hits 0, actually at 0, and comes down a little bit. It hits a minimum at x equals 2.5. Then it goes up for the rest of the interval. The maximum point is actually at 10, x equals 10. You guys have any questions about that example? Ready for a little harder one. If anybody has any questions, just let me know. I mean, I gave you this example because here's one where I'm asking you to maximize a function. And in fact, there are no local maxima of this function. In that sense, it's kind of tricky. I'm asking you to maximize something for which there are no local max. You might say, well, then how can I answer that problem if there's no local max? The answer is there's always a maximum. It'll be, if there's no interior solution, it has to be one of the corner solutions. There's only 2 corners. You can check them both. It happens to be the rightmost corner is the max. That's the solution, x equals 10. You guys could do that. If I ask you this on a quiz, I think you'll be able to do it, no problem. But tell me if I'm wrong about that. Can we go on? If no one asks any questions, I'm going on. Do example 3. Here's example 3. Want to give this one a shot? Here's a cubic function. I think you probably know that anytime you have a cubic function, if you take the derivative of it, it'll become a quadratic. Then if you want to solve a quadratic equation, you may have to use the quadratic formula, something which I strongly encourage you to know and know how to use. Here's something you may need to use the quadratic formula. Or factor. You know how to factor, then factor. But your first priority is take the derivative of the objective function and set it equal to 0. And then solve. So kind of, if anybody just gets there to that first step, why don't you let me know? And there's actually, what I would love to do is get the whole class to that first step before we go on, but I can't stop you from going on if you want to. Maybe I'll annotate. What is it here, right? 3x squared minus 30x, oops, plus 40 equals 0. You guys got this far, I hope. You might see this and say, oh crap, how am I supposed to solve this? I don't know, use the quadratic formula if you want. Also, if you find a good way to factor it, you could do that. I'm really not seeing a good way to factor it. 40 is equal to 10 times 4 or 5 times 8. Then you have to multiply by 3. This is complicated. Let's just use the quadratic formula, right? What is it? X equals negative b, which is 30, plus or minus the square root of b squared. Ooh, this is a big number, 900. Minus 4ac, that's also a big number. 4 times 3 is 12. 12 times 40 is 480. Ooh, bad. This is not going to be a perfect square underneath here. What a jerk. I gave you something that isn't rational even, because the square root is going to be make it irrational, I believe. Because hey, 900 minus 480, that's 420, isn't it? Hey, 420. That this is me being somebody who went to high school in the 1990s, where that was hilarious for some reason in the 1990s. You kids today probably just think that's ridiculous, and you are correct. Yes, but this is what you'd have to do. You'd have to solve this to even find the critical values of x. You're gonna find two, aren't you? One for the plus and one for the minus. You should actually have x equals whatever you put this into a calculator, you'll get two numbers. If I did it right. Somebody tell me, am I doing it right? Has somebody gotten numbers here for x?
I did, but I rounded the radical.
Okay,
It's 20.49.
that's okay. Give me a approximate value for x.
I get 6.42 and 1.59.
6.42 and 1.59. Is that what? Let's check in with everybody here. Jonathan has these two values. Is that what you guys have as well? Can anyone confirm or disconfirm these two values?
I got 8.4157 and 1.59.
8.4, but you got the 159. That tells us something. That's probably right if two people got it. Okay, so there's some maybe discrepancy here.
Yeah, she's right for the 8.4.
Okay, I'm going to clear my drawings if you don't mind, because I actually have the answers here. So let's go on, assuming that. Oops, I have to exit this. Here we go. Yeah. Use the calculator to get x equals 1. So good job, Amina, and half good job, Jonathan. You got one of the numbers right. What do we do now? Second order conditions, right? Notice it's a maximization. I could be tricky one of these times and actually give you a minimization. I sort of wish that maybe I had also switched it up, sometimes max, sometimes min, but because it's a max, that means the second order condition is that the second derivative is negative. The necessary is that it's negative or zero. So why don't we do that? Maybe I'll annotate again. I want to annotate this. I want to take this derivative of the derivative. That's what the second derivative is. Here's what I get, right? 6x minus 30. Don't you? 6x minus 30. But now here's the kicker. I want to take these and plug those in for x and see what I get. Let's do that. I can just tell if you put 1.58 in here, this is going to be less than 12. This is definitely going to be negative. So for this one, I'm going to make a little, I don't know what I'm going to do. I think I'm going to put a little check here by this one. Like that one's good. Although sometimes red means bad, so that doesn't make sense. But what if I plugged this one in there for x? If I did that, I can just tell that that's going to be positive, right? 8 times 6 is 48 minus 30. This is going to be a positive number. And that does not satisfy. I'll make a big X through it. This one's bad. I wish I had made this one green because green means good often. Like a check mark, a green check mark. Maybe like associated with the sound like bing. And this red X would be associated with the sound like bah. Especially if you watched Family Feud, you would associate correct answers with bing and incorrect with bah. Anyways, do you guys get what I did? This here is the second derivative, f double prime. And I plugged in what I got for x here. And this one got a green check here because once I plug this in, it's negative. That's what we want. We want f. Maybe I should undo this. Like, what does it mean to get the green check? The green check happens when if f double prime is negative, you get a green check. And if f double prime is positive, you get the red X. Okay? This is very crude, and I don't know. You guys probably think I'm weird for even doing it, but how else do you make teaching math over Zoom an interesting experience? Hard. Okay, but more importantly is that you have some understanding of what I did. Does everyone see why this one gets a green check and this one gets a red X? Please ask if you don't understand.
It would just be, if you're looking for the minimum, it would just be the other way around, right?
Yes. I'm looking for a minimum, it would be the other way around. This one would get the green check and that one would get the red X. You do not have to use checks and X's in your paper. I won't be looking at your homework and say, hey, where are the X's? Where are the checks? This person isn't using my method. I'm just making this up as I go. I do want you to know how to optimize with one choice variable. That's what this chapter is about. That's what this section is about. And I'm giving you a method, which you're free to use if you want. But yeah, to answer Kai's question, if for some reason I had given you a min here, then it would flip these conditions. Okay, I'm going to clear all of my drawings. They're great drawings. I love the color coding of them all, but I'm going to clear them. And that's because I have the answers on the next animation of my slide. Here we go. What time do I have? 12:30 to 1:45. We have another half hour. Okay. 8.42 is not a local max, so it can be ignored. but 1.58 is a local max. We don't know if it's the solution. We just know so far that it's a local max. Okay, let's look at step 3. Step 3, maybe I should have annotated again. You guys like when I annotate? What do? We're going to plug 1.58. Now we're going to plug that into here for x. And there, and there, and see what we get. We're also going to plug in the two what do you call them? Endpoints, maybe, corners. Plug 0 into there, and there, and there. And then plug 10 into there, and there, and there. You want to see what you get. This is a hot mess, some might say. But that's what we're going to do now. Step 3 is just plugging in all the possible values. No, plugging in, now we have 3 possible values. We eliminated 1, so we have 3. We have 0, 1.5, and 10. Those are the things we want to plug in and see what we get. The answer is, if you plug in 0, you get -10. That's actually pretty easy to see. If you plug in 1.58, you get 19.64. If you plug in 10, you get -110. Well, that means the answer is the interior solution. Happens to be the answer here. By the way, you didn't know that though. If let's say, for example, okay, so this one turned out to be the interior solution is the actual solution. I should have that on the last point right here. X star equals 1.58 is the maximum and solution to this problem. What if X, just to speculate, what if X had been drawn from the interval between 0 and 100? If instead of up to 10, it went up to 100, what happens to this function as X goes to 100? It actually gets really big. 100 cubed, because it has a cubed here, as X grows, it really gets, it increases, goes towards positive infinity. So as X gets big, like 100, this definitely is going to grow. And that would have been the solution. If X could be from 0 to 100, the answer would be, oh, obviously you want X equals 100. But because you can only choose up to 10 here, maximum between 0 and 10, it doesn't mean you choose 10. 10 is not the answer. The answer is 1.58. You guys see how we started here and we got to there, X star equals 1.58. Any questions about that? I'll go on if there's no questions. I'll do it. I'm going to advance. Don't make me go back there. Okay, example 4. I think that's the last. Maybe not. There's a lot of examples. Who cares? I like giving you examples. This one is literally from the textbook, section 8.4. It's problem 2D. So if you have the book, this is one of your, you can look at the other ones, 2A, 2B, 2C. I think they're all relevant, but I decided to pick this one because it was a little trickier. It has the x to the 5th. So why don't we do that? Should we do it together? Oh no, don't look at that answer. Okay. What's our method? My method is to take the derivative. What do we get? Somebody want to actually tell me what the first derivative of this is? I'll even write like f prime equals what?
Is it 5x to the 4th minus 15x squared?
Very good. This is just using the power rule here. 5x to the 4th minus 15x squared. Hopefully you guys have done this enough. You're like, okay, we get it. You move the exponent out. Whatever the former exponent was, it becomes multiplied by the term, previous expression, and you reduce the exponent by 1. That's true for both of these. That's where you get the answer. Okay, now what are we looking for? We're looking for when this is equal to 0. Remember, that's called the first order condition. Sometimes I just abbreviate it like this. The first order condition is this. This is actually a way for us to solve for x. I haven't taught you how to do a quartic. You don't know how to solve quartic equations, do you? So if you get something like this, are you going to freak out? Please don't freak out. Use your algebra background, whatever you have. Develop it in this class. Practice it. That's part of what we're doing, is practicing algebra here. We're doing calculus, but we're practicing algebra. So when you get something like this and you want to solve it, it's quartic, but you can think of factoring. Factoring is a way to simplify an algebraic expression in a way that might make it easier to solve. And in this case, it will make it easier to solve. There's something really obvious you could factor out of the left-hand side of this equation. That's x squared. So do it. Factor out an x squared. I don't say divide by x squared, but just factor out the x squared. You get 5. You see what I mean by factor out? I'm taking it like dividing out an x squared from this. I would get 5x squared minus 15. I haven't changed this at all. I've just rewritten it a different way. You agree? What I've written here and here is the same thing. I've just rewritten it in a way that makes it easier to solve this problem, which is what values of x make this equation true? That's really what we're asking. I think you can see pretty easily what value of x would make it true here. If x equals 0, clearly this is true. So what is x? X could be, a fancy way to do this here. I'll teach you guys how to look even fancier when you're doing math. Instead of saying x equals something, say x is an element of a set. And this is sort of like telling you when there's more than one possible answer, it's just a little fancier way of saying it's one of these possible things. X could be 0 because 0 solves this equation. You can kind of tell that right here because when x equals 0, the whole thing is 0. What else could x be? Well, if this part here is 0, then it's also equal to 0. When does that happen? Well, that happens when 5x squared equals 15. Well, when does 5x squared equal 15? Well, maybe you can see that quickly. If not, just sort of divide both sides by 3. You get x squared. I'm sorry for how badly this handwriting is. X squared equals 3, or x equals what? Plus or minus the square root of 3. I would encourage you in this class not to forget about the multiplicity of square roots. It's really easy to think, what's the square root of 4? 2. What's the square root of 9? 3. It's technically not correct because that's what we would call the principal square root, the positive square root, but there's always a negative number that could answer it too. So when you get to x squared equals 3, don't just say automatically x equals square root of 3. You should say plus or minus square root of 3. Okay. In fact, I'll even write both of them separately just to highlight that fact. Here we go. So there's 3 values of x that satisfy the first order condition. That's 0, negative square root of 3, and positive square root of 3. That's it. We're done with step 1. Oh, by the way, are all of these in the range? Look at our range, -1 to square root of 5. I think it's time to switch colors to red so that we can make a big red X through one of these. Which one am I going to make a big red X through? This one right here, right? And we'll even make the Family Feud incorrect sound, bah, because that can't be right. Do you guys see why that can't be right? Look at this. X has to be between -1 and the square root of 5. Well, negative the square root of 3 is like -1.73. That's smaller than -1, so that's outside of our range. So we don't even need to consider it. So that means there's only 2 values that we found in step 1. Good? Now let's clear this and go to step 2. Well, you know what? I don't want to clear everything. Some of these things can be useful. Eraser? Maybe I can erase some of this stuff. Okay. You can erase this. Hey, that's cool. All right. Yay. All right. So let's think about the second order conditions now. Oops. I want to draw. I press draw. Okay. S. Oh no, those are lines. S. If I put this on YouTube, I'll be very embarrassed that I'm making all these mistakes and talking to myself while I'm making mistakes. What is the second order condition? F double prime equals, I'll just do it. I think you guys know how to do it. So rather than wait for you to do it, I'll say it. 20x cubed, right? Minus 30x. Okay, it should be greater than 0 or less than 0?
Less than 0?
Thank you. And if it's necessary, then it's less than or equal to, right? And let's think about the necessary ones now. You know why? Because I don't want to miss one. Just like in the very first example I gave you of negative x to the fourth, if you had used the sufficient condition, you would have missed that one, that x equals 0 possibility. So yeah, so for now, let's think of this as the, if you want to put like, I don't know, do you use another letter there? Necessary second order condition, because we don't want to miss one. But there's only two things we need to check, 0 and square root of 3. Let's plug those into there. What happens if I plug 0 in there? Does it satisfy it? Yeah, I think so. 0 minus 0 is less than or equal to 0. So I'm going to give a green check to that. That actually did satisfy it, if I'm looking at it correctly. And how about square root of 3? 20, ooh, this is hard. Oh man, do we need a calculator for this? 20 times the square root of 3 cubed minus 30 times the square root of 3. You know how I can simplify this? The square root of 3 squared is 3. So this actually would become like 60, 60 times the square root of 3 minus 30 times the square root of 3. And that is definitely positive, isn't it? Which means I got to switch colors. This gets the red X. Did I do this? Did I do this too quickly? Do you guys see why the 0 gets the check and square root of 3 gets the X? When you plug square root of 3 into this, not the first derivative, but the second derivative, you actually get a positive number. If I did my math right, I would love if you guys could just check me to see if you agree with me. My math is I've used my mouse to write it here, which is why it's so illegible. I apologize for that. I used to have in my possession an Apple Pencil, and I was borrowing it from Professor Coronach, and I had to give it back to him. So I maybe should get one of my own, and then the writing would look a lot better. Anyways, what am I asking you to do? I'm asking you to speak up and tell me if for any reason you don't see how I got to this 0 having a check and this square root of 3 having an X. Because most of your faces are hidden except for Tommy. And so I can't tell if you're understanding this or not. And Tommy's looks like he's working on something. Are you doing some math?
I calculated it out and I got like 51.95. So
It's wait a second. It's hard to hear you, Kai. You said you calculated, you plugged the square root of 3 into here. Is that what you said?
yeah, with my calculator, and I got 51.95. So it would be canceled out. I understand.
Great. 51.9 is definitely greater than 0, which means we don't even need to consider it. It's definitely not a maximum because the second order conditions, the necessary second order conditions weren't met. So let's not even consider it. The only things we have to consider now are, of course, both endpoints, -1, 0, and square root of 5. Thank you, Kai, though. That is, I mean, sort of telling me that you are following along. You're getting to this conclusion, which is what I would like. I promise, like if I were there with you, I would be more like directly just kind of telling if understanding if this is all like really easy to you or really hard or good pace and you're understanding it. But it's a pandemic. Once every 100 years, we have to do this. I'm sure in 1918, when they were on their Zoom meetings, they were having the same frustrations that we were. That was a joke. Okay, let's do the last step. Or do we want to do the last step? Actually, shouldn't be that hard. The last step is plugging in -1, 0, and square root of 5 and seeing what we get. Once again, I'm going to do some erasing. And no, what do we need? We don't need this anymore. Really, we hardly need anything. We just want to keep we don't need this. Or this. Or this. X could be 0. Okay, we don't need anything. X equals 0 is a option. And -1 and 5. What is, we just have to find f of -1. See what that is equal to. F of 0. See what that's equal to. And f of the square root of 5 and see what that's equal to. Whichever one gives us the highest is the max. Hopefully you guys know how to do this. Plug in -1 to the 5th power. -1 to the 5th is -1. Minus 5 times -1 to the 3rd power is also -1. So that is equal to -1 minus 5 times -1 is actually 4, if I did it right. You guys agree? Doing all this math right here on the spot. This one's easy. 0 minus 0 equals 0. Okay, so far -1 is the winner. It's got 4. 0 is 0. Let's see what we get when we plug in square root of 5. Ugh, it's not going to be that pretty. Or is it? Ooh, I see a way to make this a lot easier to do, isn't it? Because square root of 5 squared is 5, and that's exactly what we have here as our coefficient of x cubed. So it's going to be 0. But in case you can't see that in your head, what would you do here? You would take, I'm going to pretend you didn't see that, and you have to just do this step by step. Let's remember that 5, the square root of 5 is the same as 5 raised to the 1/2 power. And if I do that, that's what I have here. 5 to the 1/2 power raised to the 5th power minus 5 times what? This is, once again, I'm going to write this as 5 to the 1/2 power raised to the 3rd. Remember how I did this thing with you guys practicing exponents? This is kind of like where it's supposed to come in handy when you have a problem like this. This equals 5 to the 5/2 power. That's because that's what this first term becomes 5 to the 5/2. How about the second term? Well, we have 5 times 5 to the 5/3, because this becomes 5. I'm sorry, 5 times 5 to the 3/2. Well, this is like 5 to the 1 times 5 to the 3/2. I'll write that out here. 5 to the 1st power times 5 to the 3/2 power. Oh my gosh, handwriting is getting worse. It's not even handwriting, it's like mouse writing. Okay, so this, now maybe you can see, this thing becomes 5 to the 5/2. They both become 5 to the 5/2. Do I have to write it out? Nobody wants to see this mouse writing. I'm doing it anyway. Equals 0. After all this, equals 0. So at -1, it's 4. At 0, it's 0. Square root of 5, it's 0. The largest of 4, 0, and 0, like the biggest of the big green checks is this one. There's our answer, -1. And you know, maybe that wasn't so obvious when you looked at this problem. Because it probably wouldn't be. Not a lot of us can picture now we have something raised to the 5th power. This is a 5th order polynomial. You know, it's not so obvious what the answer would be, but this method gets you the answer every time. It's foolproof. So the answer should be -1. You guys see how we got it? I think I have a little description of it here. The solution is x star equals -1. So if you want to see it on the slides, I have it written here too. Okay. I think if you understand this, then you're perfectly capable of doing the homework. And if you want to do it on Tuesday, you can turn it in early, but I'm still not going to make it due till Thursday, just to give you more time to work on it. Here's another way to find a solution to a problem like this. What if we had a maximization problem? Here's just a standard maximization problem. And then let's say you find a local max. So how can you find like a sufficient second order condition? So we know for certain you found a local max at x equals c, and that is inside the choice set A to B. When can we be sure that that's the solution to our problem, our original problem? The answer is, at least one answer, is that if the function f, that's the objective function f, is concave on the entire region of the interval between A and B, then the local maximum found at x equals c must be the solution. Why is that? Anybody want to try to venture a guess or an answer that sort of can explain why, if you have a local max and the function is concave, then you know it's the solution? Why is that?
I kind of just like picture it in my head.
Yeah, that's great.
Caves and A and B are both where it's like probably decreasing to C is where it has.
It's hard. I'm sorry, it's hard to make out what you're saying. Can other people?
Sorry, my connection's bad.
Am I the only one who can't understand what she's saying, or is it everyone?
No, I can't really hear
Okay,
what she's saying.
sorry, Kai. I guess it's not your fault, but yeah, you can always chat if you. She said her connection is bad. I think you were right, and here, let me try to say what I think you were saying. Is that if you imagine this graph as only possibly having one hump, one hill, there's one point at the top of the hill, there can't possibly be some other way for this function to sort of turn the other way and go up, because that would create something that's not concave. Concave means it's hill-shaped, and it's only hill-shaped. It never switches to become more bowl-shaped. That's how you know. That's the answer to why. You can just think of the shape of the graph and say, that's enough. This is a one way to prove that your answer is right. You don't even have to consider the corner solutions. Remember how the method I gave you was like step 1, step 2, step 3, step 4. Step 3 and 4 are all about, you got to check the corner solutions too to see if those might be the answers. Well, if the function's concave, then you don't have to for a maximization. That's a nice thing. And how about, let's flip it. If you're doing a minimization problem and the function is convex and you find a local min, now all those have to happen. Convex function, minimization problem, you find a local min. The nice thing is that you got an answer. You're sure that your answer is the correct answer. There's no other one you need to check. This is a nice thing. I put this on here also to preview multivariable maximization problems, because what if we're not just selecting X, but we're selecting X and Y? Like, think about this maximization problem where F is now a function of X and Y, 2 variables. And our choice variables are X and Y. And our choice set is now, wait, what's happening here? Is it a square? Is it a rectangle? It's some shape, or it's some region. We're gonna use this a lot more in the future. That says, if our objective function f is concave, and we find a local maximum of f, then we're done. We know that is actually a maximum. You don't even have to look at the corner solutions. And the reason why it's better not to have to look for the corner solutions is because once you get to more and more variables, it's not even clear what the corners are, right? The corners could be themselves be functions. And that sounds weird to say, but the boundaries could be, it could be a circle, or it could be, a triangle. There's all kinds of shapes that could be your choice set. So that's why the choice set matters. Right now, I just give you intervals because we're only talking about one dimension, but already if you go to 2 dimensions, you can imagine a lot of different shapes for the choice set. You go to 3 dimensions, oh boy, it gets really complicated. So what I have on this slide, if you already have a concept of it, because we're doing it in 1 dimension of, oh, okay, if it's concave, then we're good. That will carry over into multiple dimensions. The same concept of, oh, we found a local maximum. Is it the real answer? Yes, because the whole function is concave on this region. All right. What else do I want to tell you guys? Last problem for the day, which is good because we only have 4 minutes and I'm not even sure we'll get through this. Maybe I'll just explain it and you can think about it and we'll talk about it next class. This is also a problem from a textbook, 8.2. And it's the same thing, only with a lot of parameters in it. I just don't want you to think that what we're doing can only be done when there's numbers. It can also be done when there's parameters or exogenous variables, either one. You just have to think about what is your true choice variable. Okay, like when you see this problem, the Dutch government estimated f of x, the cost of flood damage and construction of a dike. The Netherlands is very low, and if the water level comes in, it'll stay there. It doesn't even rush to the ocean because it's a lot of it is below sea level. So these dikes are very important. But the higher you build a dike, the more expensive it is. And so this was an equation actually estimated by the government of the Netherlands to estimate the cost of flood damage. And of course, they wanted to minimize it. Here's an example of something you want to minimize. You want to minimize costs. The question is, solve for x. And consider how the optimal x star depends on P0, V, delta, or K. And so we definitely don't have time to do this today. So think about it if you want. We'll talk about it next class. I think I'm going to stop talking about it now because we'll definitely do it next class. And then we'll move on. But you can also check out homework set 2. You guys can do it. There's nothing on homework set 2 that you can't already do based on what I've told you today, if it made sense. You guys have any questions or anything? And we'll stick to what the syllabus says, which is next quiz is also on Thursday. So quiz 2 will be a week from today. Your homework set 2 and quiz 2 will be next Thursday. Have I stopped recording?